First, we're going to look at some of what we studied in Chapter 4, and then we're going to apply this idea of statistical inference so that we can see if there really is a relationship between our variables. So in Chapter 4, what we did was we discussed the linear regression, and we used linear regression lines to predict some y value for a given x. So what we're going to do in this chapter is we're going to take it a step further and do test and confidence intervals in this setting. Before you ever try to attempt any inference, the first thing that you want to do is just examine the data by making a scatter plot, identifying any outliers or any other influential points using that graph. Then you want to calculate the least squares regression line, and also you want to calculate the correlation coefficient and the coefficient of determination R squared. Now, the slope and the intercept of that least squares regression line, where our slope was b and the intercept was a, these are actually statistics. So what makes them a statistic was the fact that they are estimated based on sample data. So what we're going to do is we're going to use these estimates to estimate the parameters of the population. So the population characteristics. We're going to be looking at the true slope beta and the true intercept alpha for the entire population where our sample came from. Now also, our R is a sample statistic for the correlation, and the test that we do is actually going to also provide us with a way to test rho, which is the population parameter for correlation. Now, we won't spend much time talking about rho, but it is just an implication of what we're studying in this chapter. So, when we talk about this population regression line, it's as if we are assuming that we have the data for all of the population, and it would follow this alpha plus beta x. So we would have a true intercept and a true slope, but then there would be this little error. And this error is random. It is going to follow a particular distribution, but it's just this, the fact that we know that all of our data is not going to fall exactly on a line. So we need to have this little bit of error in our population regression line. But the ultimate thing that we need to understand right now is that this regression line that we calculate from sample data is trying to estimate what this true population regression line is. So we estimate alpha and beta using our A and B from our calculations in StatCrunch. So looking at example 15.2, a study was looking at the relationship between the birth weight and the mother's age in young mothers. And so these observations here, we have mothers between the ages of 15 and 19 and the birth weight of their babies. So let's go back to what we did in Chapter 4, where we found the equation of the estimated regression line. We start with our data in StatCrunch, and then we go to Stat, Regression, Simple Linear. Everything that we're going to do is going to be in this menu. The x variable here is x, and the y variable is y, based on the way that this data set's given. Now, later on, we're going to be exploring this hypothesis test and confidence interval, but for right now, we just want to get our estimate for the regression line. So here's our output, and here is our equation for our regression line. So the estimate for the intercept is negative 1.163, and the estimate for the slope is 0.245. Now the second question is asking us to estimate the mean birth weight of the babies born to 18-year-old mothers. And I want to remind you that if you go to Edit and you go to a prediction, we can actually predict for this 18-year-old mother by typing in 18 here. And when we do that on our output, we get this predicted value. And so our 18-year-old mother, we would expect to have 3.2493 grams as the birth weight. Now, in chapter 4, we were predicting for an individual. But in chapter 15, we actually are also interested in the mean birth weight for all 18-year-old mothers. And so the same thing, whether it's predicting for a particular individual or predicting for the mean of all of these 18 mothers, both can now be done with these same models. So it's just recognizing that when you are making predictions, you're making predictions both on an individual and for the mean. Now, be cautious, just like we were in chapter 4, of making predictions outside the range of observations. Extrapolation is extremely dangerous, and I have a typo there. It is dangerous. And extrapolation is where you would try to make an estimate outside of this range. This model isn't going to work for 13-year-old mothers. This model also is not going to work for a 23-year-old mother. Here, we're only looking at teenagers between 15 and 19. Anything beyond that is a very dangerous thing to do. Interpolation is where you're making observations and predictions within the range of values that you have. And you can feel a lot more confident that those values are going to be more accurate. Now, recall in chapter 4 that we were interested in finding R squared and the standard error. So R squared is that coefficient of determination, and it's finding the proportion of the variability in Y. I'm not sure where that went. Oh. I just typed it twice. There we go. Okay. It's the proportion of the variability in Y that can be explained by the approximate linear relationship between X and Y. Now, our SE, that's going to be that estimated standard deviation about the population regression line now. So now we're not just interested in the sample, we're interested in what's going on in the population regression line, but we'll still use that SE in order to estimate that population standard deviation. And as a reminder, this is the typical amount by which an observation deviates from the population regression line. So in example 15.3, I downloaded the elk weight from the example here, and we have the equation of the least squares regression line is given right here, where the weight Y is equal to negative 135.51 plus 2.806 times X, the girth. Now, what's the proportion of variation here? We're looking for R squared. So 0.865. And what that means is 86.5% of the variation here is explained by that least squares regression line. And then finally, if we want to find the magnitude of the typical standard deviation, here we're looking for the estimate of the error, and that's 23.66. So that's all that we did back in chapter 4. Now we want to take this a step further and look at the sampling distribution of B. So B is our estimate for the true slope. So here the mean of our sampling distribution is going to be centered around the true slope. And then the standard deviation is going to be found by calculating the standard deviation of the whole population and dividing it by the square root of the sum of all of the deviations squared. Don't worry, StatCrunch is going to handle all of this for us, but I just want you to recognize that this is a sampling distribution like we studied before. And this sampling distribution is going to be normally distributed as long as our sample size is large enough. Now, we can do confidence interval and hypothesis test for our regression slope. So the confidence interval is going to be set up very much like the way that we set up our confidence intervals for means, because we're going to take our estimate B, and then we're going to add and subtract from the t-distribution. However, this time the t-distribution has the degrees of freedom n-2. And then the standard error here is a little bit more complicated, but we need to estimate it with the standard error estimate that we have already calculated. We've seen how to do that in StatCrunch. So these confidence intervals are still giving us that same concept that we are so whatever percent confident that the true value of the slope is going to be between two particular values. So let's go back to the baby data and calculate a confidence interval there. So here I'm actually just going to edit what we had already done. And here we've been ignoring the perform, but now we're actually going to do confidence intervals. So if we want the 95% confidence interval, we do 0.95. If you wanted 99, change that to 0.99 and so forth. So click compute, and what you're going to get is now you're going to have the confidence interval for the mean. Now, I probably should have gone ahead and gotten rid of that prediction because it's also giving me the prediction interval. So let me do that real quick. Okay, we're not usually going to be doing prediction intervals are interesting, but they're not part of this course. All right, so now here we go. This is what we're interested in. So for these parameter estimates, we have the 95% lower limit and the upper limit for the intercept and for the slope. So what we're actually interested in for this problem is the slope. And so here our confidence interval states that we are 95% confident that the true slope is between 0.139 and 0.351. What's important here for us to recognize is that we're confident that it is positive. And we're confident that it's going to fall between these two values. We can do the same thing for our ELK data. And so here, if we go to options, edit, and choose the confidence interval, and let's say that we wanted to do a 99% confidence interval, here we would have our upper limit and our lower limit. The true slope, we are 99% confident that the true slope for this model is between 2.028 and 3.585. So we are again confident that it's definitely positive, and it's going to be somewhere between those two values for the entire population. We take our sample data and we look to see what value we can estimate for the population parameter. Now we also can talk about hypothesis tests. And for these hypothesis tests, the null is always going to be where you think that the true slope is going to be equal to some null value. It's typically set equal to 0. So usually you would say beta equals 0, but it really could be any value. But typically we set it equal to 0. And then your alternatives, we're either looking for the slope being greater than 0, the slope being less than 0, or the slope just not equaling 0. So here, just like before, we're always setting this equal to our parameter, and we are making our comparisons. Now, sometimes you will have beta greater than some actual number other than 0, but for the most part, these are always going to be 0. So I'm even going to make that change here, and just our null is going to be beta equals 0. If for some reason you wanted something other than 0, then you could absolutely get that calculation. But the typical questions that we're answering here is the population slope different from 0? Got another typo, you guys. Sorry about that. So is the population slope different from 0? So let's go to StatCrunch and answer that question. So now, instead of the confidence interval, I simply want to go to hypothesis test. And now here, we can do an intercept and slope, but we're just going to be interested in slope in this course. And so like I said, it's usually 0, but if you needed to test anything else, you could change that here. And then you pick your alternative. So here, we want to see if this really is a positive slope. So we're going to set that greater than 0. And when we do our output, our test statistic and our p-value. So here we get such a small p-value that we are going to reject the null, going with the alternative. So there is sufficient evidence to support the claim that the slope is in fact positive. If our p-value was not less than 0.05, then we would not have enough evidence to support that claim. We can also do this with the baby data. So if we go to options, edit, and we do our hypothesis test, and here we're just going to see if it's something, just something different from 0. Hit compute, and we get our test statistic and our p-value. And again, our test statistic is telling us how many standard deviations away from the mean we are. And so here, this is 5.34, very far away. So we would expect to have a small p-value. So again, in this example, we are confident that there really is a slope, a relationship between these two variables. Now, we don't know if it's a cause and effect relationship, but we can at least recognize that there is a relationship with these two values, or with these two variables.